The topic of this session is increasing and decreasing functions part 2. Following is a sufficient condition for a function to have a relative extremum at an interior point of an interval. It is a form of a theorem which is called first derivative test for extrema. This is for maximum or maximum. Let f be continuous on interval I, which is closed interval a comma b, and let C be an interior point of I. Assume that f is differentiable on open interval a to c and open interval c to b. Then if there is a neighborhood open interval c minus delta comma c plus delta contained in I such that f dash x is greater than equal to 0 for c minus delta less than x less than c, and f dash x is less than 0 for c less than x less than c plus delta, then f has a relative maximum at c. Here in this theorem, it is not said whether f is differentiable at c or not. It may not be differentiable at c. Also, f dash x is greater than equal to 0 for all x which lies between c minus delta and c, and f dash x is less than equal to 0 for all x lies between c and c plus delta. If these conditions are assumed, then f has a relative maximum at c. So let us see the proof. If x belongs to open interval c minus delta to c, then it follows from the mean value theorem that there exists a point cx belongs to x comma c such that fc minus fx is equal to c minus x into f dash cx. That is, we apply the mean value theorem on closed interval xc. So we got this result. Since f dash cx is greater than equal to 0 and c minus x is greater than 0 because c is greater than x, so we conclude that fc minus fx is greater than equal to 0 because c minus x is greater than 0. F dash cx is greater than equal to 0 because cx is point between x and c. So we got fx is less than fc or equal to fc for all x belongs to c minus delta comma c. That is, the value of f at c is maximum than the all other values x, the value of f at all other values x, where x belongs to c minus delta to c. Similarly, if x belongs to c comma c plus delta, then it follows from mean value theorem that there exists a point cx which belongs to c comma x such that fx minus fc is equal to x minus c into f dash cx. That is, here we apply the mean value theorem to close interval c comma x. Since f dash cx is less than 0 and x minus c is greater than 0, so this is less than 0, this is greater than 0, so we conclude that fx minus fc is less than equal to 0. That is, fx is less than or equal to fc for all x belongs to c comma c plus delta. That is, f has maximum value at c compared to any other value x on where x belongs to open interval c to c plus delta, so that f has a relative maximum at c. That's the proof. Now similarly, first derivative test for extrema, we are taking the case of minimum. Let f be continuous on the interval I, which is closed interval a to b, and let c be an interior point of I. Assume that f is differentiable on open interval a to c and c to b. Then if there is a neighborhood c minus delta c plus delta contained in I such that f dash x is less than equal to 0 for all x lies between c minus delta to c, and f dash x is greater than equal to 0 for all x lies between c to c plus delta, then f has a relative minimum at c. The proof is similar to the proof of relative maximum. Now let us see the example. Find the points of relative extrema of the function fx is equal to modulus x square minus 1 on the domain minus 4 less than equal to x less than 4. That is, fx is equal to modulus x square minus 1 on the domain close interval minus 4 to 4. Let us see the solution. We have fx is equal to x square minus 1 if x belongs to close interval minus 4 to minus 1 union 1 to 4, and minus of x square minus 1 if x belongs to close interval minus 1 to 1. This is obtained by applying the definition of modulus of x. And when we find the derivative of this, it gives 2x if x belongs to close interval minus 4 to minus 1 union 1 to 4, and minus 2x if x belongs to minus 1 to 1. Now f dash x is equal to 0 implies x is equal to 0. So we shall check for extrema at points x is equal to 0, minus 1, 1, minus 4 and 4. So these points divide whole real line or our domain minus 4 to 4 into these parts minus 4 to minus 1, minus 1 to 0, 0 to 1, 1 to 4. So we'll see the behavior of function at these points and we'll check whether it is having extrema on these points or not. So at x is equal to minus 1, let us take delta is equal to 0.5. So by this way we can take. Then if x belongs to minus 1 minus 0.5 comma minus 1, that is open interval minus 1.5 to minus 1, then f dash x is equal to 2x and x lies in this interval. So f dash x is equal to 2x is less than 0. And if x belongs to minus 1 comma minus 1 plus 0.5, which is equal to minus 1 comma minus 0.5, then f dash x is equal to minus 2x and x lies in this interval. So f dash x is equal to minus 2x is greater than 0. So as f dash x is less than 0 in the small neighborhood, minus 1.5 to minus 1 and f dash x is greater than 0 in minus 1 to minus 0.5. So function fx has relative minima at point minus 1 because according to our theorem f dash x is less than 0 in minus 1.5 to minus 1 and f dash x is greater than 0 from minus 1 to minus 0.5. So the function fx has relative minima at x is equal to minus 1. Now at x is equal to 0, taking delta is equal to 0.5. So this will be the situation. Then if x belongs to this interval 0 minus 0.5 comma 0, that is minus 0.5 to 0, then f dash x is equal to minus 2x and x lies in this interval, so x is negative, so total this quantity is greater than 0. Then if x belongs to then 0 comma 0 plus 0.5, that is 0 comma 0.5, then f dash x is equal to minus 2x and x lies in this interval, that's why this f dash x is less than 0. So we got that as f dash x is greater than 0 in minus 0.5 to 0 in this interval and f dash x is less than 0 in 0 to 0.5. So function fx has relative maxima at x is equal to 0. So at x is equal to 0, the function will have maxima. Now let us talk about the point x is equal to 1, taking again delta is equal to 0.5. So this will be the situation. Then if x belongs to 1 minus 0.5 to 1, that is 0.5 to 1 in this interval, then f dash x is equal to minus 2x, which is less than 0 because x belongs to 0.5 to 1. So minus 2x is less than 0. And if x belongs to 1 comma 1 plus 0.5, that is 1 comma 1.5, that is x lies in this interval, then f dash x, which is equal to 2x, is greater than 0. So as f dash x is less than 0 in 0.5 to 1 in this interval, and f dash x is greater than 0 in 1 to 1.5, so function fx has relative minima at x is equal to 1. Also, using the definition of relative maxima, by taking small neighborhood v of 4 and minus 4, we observe that fx has relative maxima at minus 4 and 4. So this is the approximate graph of this function. You can see at 4 it is having relative maxima, at minus 1 it is having relative minima, at 0 it is having relative maxima, at minus 1 at 1 it is having relative minima, and at 4 again it is having relative maxima. Thank you.